Okay, we were discussing topics on inequalities, right? And in our last class, we have proved the Cauchy squares inequality. We are going to continue from where we left in our last class. Uh, now we are moving on to section 7 or type 7 inequality in the chapter of the book by Barner and Child. And here they are claiming that if A1, A2 up to some an are n number of positive numbers and not all equal to one another. Then the idea is what they're claiming is n times sum over ar to the power x plus y is actually greater than sum over ar to the power x, sum over ar to the power y, and the summations are for r equals to 1 to up to n. Or, okay, let me write according as x and y have same or opposite sign. So there is a dependence on x and y being same sign or opposite sign, and depending on that, we are going to have two different versions of the inequality, and the other version is this. So when they are of same sign, we're going to get greater than, but when they are of opposite sign, we're going to get less than. Let's try to prove the idea. If we can prove it, it will be an important result. All right. So we are going to assume case by case basis. Case 1 is x and y have same sign. That means we are going to prove that greater than 1, right? So let us choose r and s be two integers from the list of integers 1, 2 up to n. Okay. Now here is an interesting claim. That is, the claim is ar to the power x minus as to the power x and ar to the power y minus as to the power y. These two expressions are both either both positive or both negative or both equal to 0. Why is this true? Okay, so the thing is, we have three possibilities. X is greater than y, x is less than y, and x is equal to y, right? So even though we have assumed that x and y have same sign, there is no guarantee that they are not equal. They're equal, right? So even though both are of same sign, we can still have all three cases. Now, assume x greater than y first. If x is greater than y, and okay, All right. Basically, I am not interested in comparison between X and Y. Rather, I'm interested in comparing AR and AS. So AR greater than AS, AR less than AS, and AR equal to AS. Let's consider all these three cases. First, if AR is greater than AS, then AR to the this would mean actually AR to the power X is greater than AS to the power X, which would mean AR to the power X minus AS to the power X is positive. But it would also mean that AR to the power Y is also greater than AS to the power Y, taking power Y on both sides of the inequality. That would mean this guy is also positive. Similarly, if we assume that AR is less than AS, then both of them are going to be negative, right? And if we assume the very special case AR is equal to AS, then both of them are going to be equal to 0. So these two expressions in these two boxes cannot have opposite signs. If and in case they do not have any signs, one of them do not have any sign, that is one of them is equal to 0, then the other one is going to be 0 as well. So they share the same polarity, that's for sure, in every case. Now, this would mean if I multiply AR to the power X minus AS to the power X, and the term AR to the power Y minus AS to the power Y, then since they're of same sign, this is going to be greater than 0. And in case they're equal to 0 both, we are going to have the equality. So this is the inequality that we are going to work on to complete our proof. So in our next page, let's just rewrite this equation: AR to the power X minus AS to the power X times AR to the power Y minus AS to the power Y greater than equal to 0. Let's multiply everything. So we have the first term is AR to the power X times AR to the power Y. So AR to the power X plus Y minus AR to the power X, AS to the power Y minus AS to the power X, AR to the power, and finally the last term is going to be positive, plus AS to the power X, AS to the power Y is greater or equal to 0. Please let me know if you have any confusion anywhere up to this point. If there is not, then I'm moving on. So let me keep the positive terms on the left hand side. The terms with positive sign. So AR to the power X plus Y. And you can see that we have AS to the power X plus Y here as well. So AS to the power X plus Y. This is also a term with positive sign. And transfer the negative ones on to the right hand side to get AR to the power X, AS to the power Y, plus AS to the power X, AR to the power Y. Now, recall that R and S are two integers from this list. And I am not considering the case where I have chosen the same integer for R and S. So we are choosing an ordered pair in a way, right? So we're choosing two unequal integers from this list actually. Now, so since R and S are chosen from this list and R is not equals to S, if you consider this, then you can understand that here we do not really have just one inequality. Technically, we have multiple inequalities. For different choices of R and S, we have different inequalities. How many choices of R and S are there actually? How many ways can you choose two integers from this list? Can anyone tell me? Shouldn't it be NC2?
N square, N square. No,
Not
okay,
really,
NC.
because R is not equal to S. That is why it's not n
Yeah,
square, but n into n minus
yeah,
1. So,
NC2, yes.
all right. So we have NC2 number of different inequalities here. So adding, let's choose this. It is denote this inequality by star. So star is not a single inequality, but rather a collection of NC2 number of inequalities. Adding all NC2 possible inequalities in star, we get, what do we get? Okay, first of all, the right hand side is pretty straightforward, I think. Let's write the right hand side. We have technically we have r equals to 1 up to n, s equals to 1 up to n. Just one additional condition, s is not going to be equal to r. So all such terms, ar to the power x, as to the power y, and that's it. If you add, you do not really have to write both terms. You should be able to understand that, because um, consider this. If you choose r equals to 1, s equals to 2, then right hand side is a1 to the power x, a2 to the power y, and plus a2 to the power x, a1 to the power y, right? So you counted both of the cases, both of the combinations switching x and y, right? So both of them are already counted here. Now, for example, if you choose r equals to 2, s equals to 1, are we going to choose it? This is not going to be, if I already count r equals to 1 and s equals to 2, I'm not going to count r equals to 2 and s equals to 1 anymore, because we have used NC2, not NP2. So the pairs are not ordered. So 1 comma 2 and 2 comma 1, not both of them are going to be counted. One of them only are going to be counted. One of them only is going to be counted. That is why if we count r equals to 1, s equals to 2 once, we are not going to count r equals to 2 and s equals to 1 anymore. So in that case, no double counting is going to be applied, and we have both the terms a1 to the power sum 1 and a2 to the power sum 1 for switching a1 and a2, right? That is why if you just write one term here, it would work, first of all. Now, secondly, let's focus on the left hand side, but let me know if anyone, and if there is any confusion in understanding why we have just one term here. All right, no confusion. That's great. Now let's focus on the left hand side. Here, this is going to be interesting. Uh, for r equals to 1, s equals to 2, what is the left hand side? It's a1 to the power x plus y plus a2 to the power x plus 1. For r equals to 1, s equals to 3, which is another choice, right? So for this choice, left hand side is going to be a1 to the power x plus y plus a3 to the power x plus y. So you can see already that a1 to the power x plus y is repeated. And it is not repeated just twice. How many times is it going to be repeated? Can anyone tell me? If you choose r equals to 1, think like this. Think in combinatorial way. If you choose r equals to 1, s is not going to be 1 ever, right? So what are the if you fix r equals to 1, what are the choices for s? They are from 2 up to
N
n.
minus 1.
N minus 1. So we can guarantee that a1 to the power x plus y is going to be repeated overall n minus 1 number. We are going to have n minus 1 number of a1 to the power x plus y. And the argument is same for a2 as well. We are going to get, if you choose r equals to 2, s will run from 1 up to n, skipping just s equals to 2. So each ai is going to occur exactly n minus 1 times on the left hand side. So we are going to have ar to the power x plus y sum r equals to 1 up to n times n minus 1. So let me write this inequality one more time here. N minus 1 sum r equals to 1 up to n ar to the power x plus y is greater or equal to r equals to 1 up to n and s equals to 1 up to n. Okay. Okay. I think I have done a little mistake here. That is, for let's choose examples. For r equals to 1, we are going to count s equals to 2 at some point. The only restriction is s cannot be equal to r. So if you choose r equal to 1, at some point, s is going to be 2. S is never going to be 1, but s is going to take all other values. But when you get to r equals to 2, s will start from 1 again. So r equals to 1 and s equals to 2, and r equals to 2, s equals to 1, both are going to be counted if I write the summation in this manner. So I need to do something here to make it right. That is why one simple change will do actually. Just I think if you start the summation from r plus 1, it will be enough. That will make sure that we are not over counting anything. So I did the very mistake that I warned you about, right? Okay, so let's make the correction here as well. S runs from r plus 1 up to n, and the term is ar to the power x, as to the power y. Let's see. All right, okay. So now let's do some rearrangements. Multiply this n minus 1 to this expression here. So we have n times the sum.
So I have a question.
Sure, sure.
So in this case, r can be n and x2 can be n. And in that case, r will be equal to x.
You are
So if r is
considering the case that at some point r is equal to n and s equals to
s is also equal to n. So in that case,
if
r is equal to x.
okay, if at some point when the sum of r runs up to the exact last end, that is r equals to n, this sum will not run at all because the starting point is n plus 1. You cannot start from n plus 1 if the last end is n. So when r equals to n, s is not going to be anything. So we do not have
So
a term in that case.
I get it.
Okay, all right. So here what I was talking about, multiply n to this entire thing minus 1 times this entire thing, and I'm going to transfer that. Okay, let's write the term first. R equals to 1 up to n, ar to the power x plus y greater or equal to r equals to 1 up to n, s equals to r plus 1 up to n, ar to the power x, as to the power y. Okay. Now I'm going to transfer this term to the right hand side to get n times sum r equals to 1 to n ar to the power x plus y is greater or equal sum r equals to 1 up to n ar to the power x plus y plus sum r equals to 1 up to n, s equals to n plus 1, sorry, r plus 1, r plus 1 to n, ar to the power x, ay, sorry, as to the power y. Okay, now focus on the right hand side. I'm going to do something interesting here actually. R equals to 1 to n. Let's write this guy as ar to the power x times as to the power, I'm sorry, ar to the power y, and uh, okay, plus sum r equals to 1 up to n, sum is equals to r plus 1 to n, ar to the power x is y. Okay. Hmm. Give me a moment, please. Uh, I got to a point where I do not have what I wanted. So please let me do a very quick revise of what I did so far. Okay. I think I did the correct thing on at the first time because, okay, let me do a revise loudly actually. So I have made sure that we have AR n minus 1 times. And how did I make sure of that? If R, if I choose R, for example, let's choose another. Say if R equals to 6, then S runs from 1 up to n, but S is just not equal to 6. This is how I made sure that I am going to get a 6 n minus 1 times, where 6 is just a particular random choice of R, right? So 1, choosing R equals to 1, S at some point becomes 2. So when I choose R equals to 2, if I do not let S to be 1 at any point, then okay, that's it. Uh, I got A1. Okay, I think okay, uh, let's restate. Choose R equals to 1. If R equals to 1 is chosen, S is from 2 to n, so there are n minus 1 choices of S. Then choose R equals to 2 again. If I start S from 3, then S runs from 3 to n, and in that case, we have just n minus 2 number of choices of S here. So this this argument breaks down that we are going to get each AR exactly n minus 1 times. That is why it was correct at the first time. So I'm extremely sorry for that. So let's write S equals to 1 up to n. S is just not equals to R. So it was correct the first time. So just making the corrections in the indices will do. So S is 1 up to n. S just not equals to R. 1 up to n. S not equals to R. 1 up to S not equals to R. S not equals to. All right. Okay. So what we have here is Okay, if I just write AR to the power X, AS to the power Y. Let me write first. R equals to 1 up to N, S equals to 1 up to N, S not equals to R, AR to the power S, X is okay. So what I did here, okay, what I did here is I replaced this R by an S, and I just wrote S and R instead of one sigma notation here. I introduced two sigma notations where S runs from 1 up to N, R runs from 1 up to N. I cannot do that, of course. Of course, I cannot do that. But what if I just write a small statement, S has to be equal to R? Then it would mean that this summation is meaningless. There is no point writing this summation because S is going to have just one specific value, S equals to R. And then this entire sigma notation is going to be, cancelled actually, removed from the picture. And we just consider S equals to R. That would mean exactly what was written in the last line. So I can do that, right? So it may look unnecessary at this point, but it's actually not. Let me show you why. Let's write the next sentence here. So you can see that R runs from 1 up to N on both the terms. That is why I can do this. I can just write R runs from 1 up to N, and inside I have a summation. Okay, before that, let's do this. So technically, I have two expressions here. Let me use another color. So I have two expressions here. One is this, and the other is this. They are basically same expressions and same summations. The only difference is in one we considered S not equal to R, and in other we considered the cases where S were equal to R. So in a way, we actually covered all the cases R1 up to N, S1 up to N, AR to the power X, AS to the power Y. We just covered basically every situation. Both cases where S and R are equal and cases where S and R are not equal. So technically we've covered all cases. Now, since R is, we do not have any AR here and we do not have any AS here, they are independent. That is why I can just do this. R equals to 1 up to N, AR to the power X, and S equals to 1 up to N, AS to the power Y. I can just do this. And here comes the most interesting part. Since this is an independent summation, the index does not really matter. It is actually a dummy. So that is why I can just write R equals to 1 up to N, AR to the power X, summation, replace S by R. So R equals to 1 up to N, AR to the power Y. We started from here, we ended here. So let's rewrite what we got. We got N times summation AR to the power X, AR to the power X plus Y is actually, we have greater or equal to, right? So greater or equal to sum AR to the power X, sum AR to the power Y. All the summations run over the index R from 1 to any. Okay, I have to write N because I have N here. So now this is just case 1. Please let me know if you have any kind of confusion anywhere in the proof for case 1. All right. Now, case 2 is x and y have opposite signs, right? If x and y have opposite signs, this would mean that what are the differences we are going to observe? If you have now, similarly, if you have AR greater than AS, just like before, it would mean AR to the power X is greater than AS to the power Y. Say, for example, without loss of generality, we are, okay, let's write in a more formal tone, case 2. So X and Y have opposite sign. Okay, if they have opposite signs, then without loss of generality, let x is the one which is positive and y is the one which is negative, then AR greater than AS would mean AR to the power X is greater than AS to the power X, but AR to the power, if you compare AR and AS to the power Y, since this is a negative power, it would mean we are taking the reciprocal on both sides of the inequality. So this actually becomes less than now. So AR to the power X minus AS to the power X is positive, but AR to the power Y minus AS to the power Y is going to be negative. So the product is going to be negative. So this expression, this here, we are going to have less or equal to, and that is why all the signs are going to be reversed. So using similar logic, we can, in this case, prove that actually uh, what we got here, just sign reversed. N times sum AR to the power X plus Y is less or equal to sum AR to the power X, AR to the sum AR to the power Y. So that actually completes our proof. Please let me know if I have to repeat any place in the proof. All right. Now, we are going to generalize the result we got here. So the line here, if you divide by n square on both sides, we are going to get summation AR to the, let's write the terms first. We have, I think, less than, greater than equal, right? This is case 1. Similar argument will be proposed for case 2, right? So we have the terms AR to the power X, we have the term AR to the power Y, R equals to 1 up to N, R equals to 1 up to N, R equals to 1 up to N. Now, if I divide by n square on both sides, one of the n's are going to be cancelled because of this n. The other will remain on the left hand side. So here n, and on the right hand side there is no n to get cancelled. So we have n square on the on denominator. Put one n here and the other n here. Now observe this and generalize this result. Then we would, this is also actually true, that AR to the power X plus Y plus Z plus dot 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 divided by n is actually greater or equal to summation of AR to the power X by n summation of AR to the power Y by n summation of AR to the power Z by n, and so on. So in the similar manner, case 2 can be generalized. The only difference is going to be this symbol, right? So this is actually a generalized result, and uh, this result is generally used to solve different interesting problems, and we are going to actually prove another result that uses this result, but there is an issue. As I mentioned at the beginning of my class, I was having problem with my regular Zoom account, uh, and that is why I had to log into my other Zoom account, and that is not that does not support more than 40 minutes. That is why this meeting is going to be terminated in 2 minutes. That is why I'm going to post another Zoom link in Discord. Please join that Zoom link. I'm posting it within a minute. So I'm going to stop the meeting here and continue in our next meeting. Okay, as I was saying, we developed a very important result, and we are going to use that result to prove another important result, and that result is actually section 9 of the inequality chapter, and the result is this: if A is any positive number except 1, and xy are positive rational numbers, then the claim is a to the power x minus 1 by x is actually greater than a to the power y minus 1 by y if it is given that x is greater than y. So this is the result that we're going to prove. We're going to prove using the result we already proved in our last Zoom meeting. Now, can you see that the claim is actually the function f of x equals to a to the power x minus 1 by x is increasing, because I'm because if for greater value of x, f of x is greater. This is what all the statement is claiming. So this is a pretty straightforward claim. We need to prove that this function is increasing. And first, we are going to prove a simpler case, a special case, where suppose x equals to p and y equals to q, where pq are positive integers. So we are going to prove the result for integers first, then we are going to generalize to rationals. So now if basically if p is greater than 1, then concentrate on this expression a to the power p minus 1 by p. We are dealing with integers only. So the immediate integer that this particular p follows is just p minus 1. So I'm going to subtract that, the expression for that value, that is p minus 1. And I'm going to prove that eventually this is actually greater than 0. This would mean that at least for integer case, two consecutive expressions difference is greater than 0 means if you increase the value of x, where x is integer, you have to increase by 1 at least, because we're dealing with integers. So if you increase the value of x, the expression will be increased. This is what we are going to prove for now. Now, I cannot write greater than equal to 0 yet. Now, let's start with this and simplify the expression. So the LCM is p times p minus 1. Okay, so a to the power p minus 1 times p minus 1 minus a to the power p minus 1 minus 1 times p. Now we need to do some simplifications. So let's multiply p times a to the power p minus p minus a to the power p plus 1 minus p times a to the power p minus 1 minus and minus plus p. So some cancelling here. So p gets cancelled. So let's combine these two terms to write, take p as a common man out, a to the power p minus a to the power p minus 1. In fact, there are more guys common. So let's, a to the power p minus 1 is also common. So we are left with a minus 1. And we have here minus a to the power p minus 1, and we have p times p minus 1 here. So now what we are going to do is expand this guy in the in this binomial expansion. Actually not binomial expansion, but we are going to use the formula. If a to the power p minus 1 is divided by a minus 1, the remainder is not, the quotient is a to the power p minus 1 minus etc etc. So we are going to use this in the next line. So what was the left hand side? A to the power p minus 1 by p minus a to the power p minus 1 minus 1 by p minus 1. And this so far is equal to p times p minus 1. We have a p here. We have a to the power p minus 1 into a minus 1 minus, as I was saying, a to the power p minus 1 can be written as a minus 1 times a to the power p minus 1 plus a to the power p minus 2 plus a to the power p minus 3. At some point, I'm going to get a square plus a plus 1. Okay, so we have a minus 1 here. We have a minus 1 here. So we can take this out, a minus 1. We are left with p times a to the power p minus 1 minus this series a to the power p minus 1, a to the power p minus 2 plus a plus 1. And we have p times p minus 1 here. We are going to do something interesting now. A minus 1, p minus 1. So how many terms are there in this series? Starting at the end, we have a to the power 0. At the beginning, we have a to the power p minus 1. So there are p terms. And how many a to the power p minus 1s do we have? Also p number of a to the power p minus 1s, right? So we are going to pair. We are going to pair with. Okay. Now it gets a little simplified actually, because we have a to the power p minus 1 here and here as well. So one a to the power p minus 1 is reduced. So we have p minus 1 number of a to the power p minus 1, and the remaining are starting from a to the power p minus 2, then a to the power p minus 3, finally a. Okay. Here is the interesting calculation part. So we have p minus 1 number of a to the power p minus 1, and we also have p minus 1 number of terms here. So we are going to couple with each term 1 a to the power p minus 1. So we are going to write a to the power p minus 1 minus a to the power p minus 2. So this term is already used, and 1 a to the power p minus 1 is used. Now we are going to write a to negative a to the power p minus 3, and with it we are going to couple 1 a to the power p minus 1. So 2 of the a to the power p minus 1s are used up, and 2 of the terms are written already, and we are going to add 1 a to the power p minus 1 to each of the term in this sequence in the first bracket. So finally, eventually, we're going to get a to the power p minus 1 minus a. And the last term is going to be a to the power p minus 1 minus 1. And that's it. Now, the thing is, recall that a has a condition. A is a positive number except 1. So, if a is any positive number except 1, then if a is 1, then this expression is just 1 to the power p minus 1 minus 1 to the power p minus 2, which is just 0. In fact, each of them is going to be 0. Not only that, this a minus 1 is going to be 0 as well. But we are actually skipping 1, right? So a is something that is not 1, but a is positive. In that case, a positive number raised to the power, choose any positive number. Choose any positive number a and think about this term. We have a to the power p minus 1 minus a to the power p minus 2. So this power is lesser than this power. So what is this expression going to be? Is it going to be positive or negative? It actually depends if a is less or greater than 1, right? So if you know that a is greater than 1, then this is going to be positive, because a number greater than 1 raised to the power bigger power means bigger expression. But if a is less than 1, then this same expression is going to be less than 0. So, and this applies for not only this term, but each of these terms, because we have a greater power here that is guaranteed. We have a greater power at the beginning of each first bracket, right? So this entire expression is going to be, each of these expression is going to be positive if we know for sure that a is greater than 1. And in that case, a minus 1 is also positive. So we can say that this expression is positive if a is greater than 1. But what if a is less than 1? Then this expression is negative. Each of these expressions is going to be negative. Sum of negative is a negative. And also look here, a minus 1 is also negative if a is less than 1. So negative times positive is positive. That means even if a is less than 1, this expression is still positive. And we are left with a equals to 1, and we do not have to care for a equals to 1, because the statement actually tells us to skip a equals to 1. So for both case, this expression is positive. That means the expression we started with is positive, which would actually mean that a to the power p minus 1 by p is greater than a to the power p minus 1 minus 1 by p minus 1, which
So I have a
means we
question.
have, sure.
I didn't get the part where a is less than 1.
Okay. Think of a number less than 1 and think of a power, for example, 7. Here you can see that p minus 1 is just 1 more than p minus 2.
And
So
so
if
a is greater than 0. A is positive, right?
a is positive,
Okay, then that's it. I get it now.
okay, yeah, here a is any positive number except 1. So yeah, now I think you are clear. So we
Yes,
have
sir.
proved the claim for integer powers. We are yet to prove the original claim, which states the statement for rational powers, but we can do that just by using the case of integers like this. Now, if x and y are fractions, then x equals to, then we can take x equals to, I know fractions are of the form p by q, right? So x can be written in the form p by l, I mean p dash by l, say for example, and y can be written in the form q dash by r. But then again, we can just multiply by common factors to both numerators and denominators so that the denominators of x and y match. So we are going to avoid such expression and consider expression with common denominators, that is p by d and q by d. We can always do that, right? For example, if you have 1/3 and 1/3, two fractions, you can just multiply by 4 here to get 4 by 12 and multiply by 3 here to get 9 by 12 so that the denominators now match. We can always do that. So we have done that treatment to x and y. Then what we need to prove is a to the power p by d minus 1 by p by d is greater than a to the power q by d minus 1 by q by d. This is what we need to prove, right? But can you see that we can just assume a to the power 1 by d equals to some b, so that the statement that we need to prove becomes b to the power p minus 1 by p is greater than b to the power q minus 1 by q. And here p, q are integers, so this result is already known due to the ideas we proved here, right? So we already know that our claim is true for integers. So this is true, which would mean that this is also true. And the fact that a is positive except 1 remains unchanged after this transformation as well. That is, b is, if a is a positive number except 1, then b is also a positive number except 1. So proving the claim for integers actually helped a lot to prove the case for general case, that is rationals very much, right? Now we can deduce some other situations, like, for example, what we just proved is if a is positive, is not equal to 1, then we prove that a to the power x minus 1 by x increases as x increases. This is what we proved. Now replace a by 1 over a. Then the statement means 1 over a is positive, which would mean a is still positive. 1 over a is not equals to 1, which would mean a is not equal to 1. 1 over a to the power, okay, let's write what we have directly first. So we have 1 over a greater than 0, 1 over a not equals to 1, 1 over a whole to the power x minus 1 by x increases as x increases. So this would mean just a is positive. This would mean a is not 1. And this would mean a to the power minus x minus 1 by x increases as x increases. So which would mean if I multiply by, I think I can multiply by minus, to take the negative of the expression. So 1 minus a to the power minus x by x, this decreases as x increases, right? Now modify further, replace x by 1 over x. Now x was irrational before, x is still irrational if you even take the reciprocal. So use the idea here we just proved. A is still positive, a is not 1, and 1 minus a to the power minus 1 over x divided by 1 over x decreases as 1 over x increases. This expression simplifies to x times 1 minus a to the power negative 1 over x decreases as 1 over x increasing means x decreasing. So it would just mean if you increase x, then this expression would also increase. So this idea can be used to solve a very interesting problem, which is the last thing we are going to do in today's lecture. The problem statement is, if a is greater than 1, n is greater than equal to 1, then prove that n times a to the power 1 over n minus 1 is greater than 1 minus 1 over a. And to solve this problem, we are going to use this last part. Let's see how. We're going to prove the case n is greater than 1 first. First, assume n is greater than 1. Then the expression n times a to the power 1 over n minus 1. Take a to the power 1 over n common. So write that at the left. Then we are left with 1 minus a to the power negative 1 over n, which matches this expression, which matches with this expression. Only this part, of course. Now, n is greater than 1. So if you consider 1 as an integer and n as another integer greater than the first integer 1, then what is this expression if you put n equals to 1? It's just 1 into 1 minus a to the power minus 1 by 1. Now n is bigger, and as claimed here, if x increases, this expression increases. Since n is something bigger than this guy 1, this expression has to be bigger than this expression, and we have this common factor has to be balanced here. So this is because n is greater than 1. Now, again, since a is something greater than 1, this is also greater than 1. So that is why this expression is even further greater than 1 minus a inverse 1. So because this guy is actually greater than 1. So what we have proved is exactly what we were needed to prove. This is greater than 1 minus 1 over a. But we neglected a case n equal to 1. So we are going to include that case now. If n is exactly equal to 1, then we need to prove that what is the expression for n equals to 1? What is the inequality? It's a to the power 1 minus 1 is greater than 1 minus 1 over a. This is what we need to prove. Now let's apply the grand principle of back calculation. If we can manage to prove that, let's multiply the a on both sides, right? So a times a minus 1 is greater than a minus 1. And this would be true if we just had, we have a square minus a here. Transfer this to the left, so minus 2a plus 1 greater than 0. And this would be true if we just had a minus 1 whole square greater than 0. And since a is something greater than 1, a minus 1 whole square is definitely greater than 0. So now consider the forward direction, and we are done. Therefore, for all n greater than equal to 1, we have proved that n times a to the power 1 over n minus 1 is greater than 1 minus 1 over a. Now we have one problem with this problem, and that problem is, are we going to remember, do we need to remember this as a theorem? If we don't, then solving this problem would be very difficult during exams, right? So even if you remember, even if you remember this result, even then we have not really used that result directly, but rather we have used the the version of the idea is pretty much it's not it's pretty distant from the original idea, right? It doesn't look anything similar to what we started with. So uh, we need to remember this one to solve the problem, and that would be difficult because there are so many things to remember. It would be impossible to remember so many things. That is why if I put any question of such sort, then I would make the question look like this. That is, first I will state this idea and ask you to prove this. Then I would ask to prove this problem. So in between, you would have to uh, come up to this point and then use this result, so that you do not have to remember anything. If you have the skill sets to solve such problems, you will be able to do that. Of course, since I have asked you to prove this part before asking you to solve the problem, it's evident that this result is going to be needed. So even if you fail to prove this idea during the exam, you can just use it to solve this problem. Please let me know if there is any confusion anywhere, or if you have any questions. All right, then that would be all for today. I'm going to end the meeting. But first, I'm going to stop the recording.